This video is going to show some load transfer from a rigid dynamics model into static structural to get some stress in the parts of this mechanism. And in the mechanism, we see there's some items that have been named. I can assign, say, aluminum to all those materials first. Because it's in rigid dynamics, they're all rigid stiffness, so there's no flexible bodies. We're just here to get forces in the mechanism, which will transfer later to static structural. And the key item here is to do just say the top half. So what I'll do is pick a few bodies to keep in the model, and the rest will be suppressed. So I'll suppress all other bodies. And then here we'll build some joints. First we need a joint to ground to represent the the motor driven crank, and so we're going to change the body to body ground and pick this as the reference location. And we're going to do another joint to ground, and that is this, and you have to be going to ground and then pick this. And so there's another. I'll change them all to revolute to ground, and then there's a few body to body settings. So we will insert two more joints, and that is a joint. We'll pick this surface here as the reference, and then this surface here as the mobile, and that will be a revolute as well. This one, another joint, insert joint. This will be reference, and this will be mobile. It's somewhat arbitrary which side you want. It's just depends on a sign convention and where you want the coordinate frame to show up. So all of these are revolutes, so I can pick them in one go and flip them over. And one of them is going to be a joint that will get a load to drive the motion, which is this. And so we drop that joint on here to get a load, and the load is going to be a rotation load, and the rotation will be 20 degrees, and that will cause the crank to rotate. And we want another load in the model, which is force here to push against. So we'll insert a remote displacement, a remote force I should say, and that remote force will have a 20 Newton load, and the direction will be opposite to that. It'll be pushing on the finger. So there's our load, there's our input motion. Under analysis settings, if we decide we want to do 50 milliseconds, maybe 100 milliseconds, we can tell it. We don't need every thousandths of a second output, so we'll knock that down to 20 equally spaced points and go ahead and solve. And that just took less than a minute, and so it has solved, and we can play those 20 frames back. There's 22 simulation frames, so if we play those back, we didn't get that quite right, and that is because I didn't set up the rotation correctly. Let me delete. Let me set 0 here, and we don't need an intermediate position and 20 degrees of rotation there. So I'll go ahead and solve that now. What happened is it put a 20 in at 0, and so it jumped forward and sat there, which isn't what I wanted to see. I wanted to see the animation, and that is now what I want. And in the next video, we'll transfer the, well, first we'll measure some of the forces. If I want to know the force going through, say, this joint, I can ask for output by dropping it on solution, getting a joint probe for that, and evaluate those results. So here's the graph, and I'm interested in, say, the total force. Total force ramps up from 57 to 104 newtons as the angle changes to push against that constant 20 Newton load. And this load is what I'm going to transfer into static structural in the next video to calculate the stress in this part, and then maybe later the stress in this part, which would have the equal and opposite force plus the 20 newtons that's on the body. So catch you in the next video.